Yes. Okay. So yeah, so we were looking at the expressive power of LTL. So what we saw is that given an LTL formula, you can construct an NVW, right? So essentially, like we know that the language corresponding to an LTL formula, it's an omega regular language. But what we also saw is that there are omega regular languages which cannot be expressed using LTL, right? So for that, we were defining this notion of non-counting languages. So a language is non-counting if there exists an n0 such that for every n greater than equal to n0 and for every finite strings uv and an infinite string x, we have that uvn x belongs to L if and only if uvn plus 1 x belongs to L, right? Yeah. So, and then we saw some examples of languages which are, which are non-counting as well as some languages which are not non-counting. So, for example, this language where the set of words such that the word has infinitely many ones. So, we saw that this is non-counting, whereas the language where you have like even number of zeros followed by ones, right? Infinitely many ones followed by that even number of zeros. So this is what we found that this is indeed not non-counting. And what we saw that like every LTL formula, it corresponds to a non-counting language. And so what it would essentially mean is that this particular language you cannot express using LTL, right? And we also saw that this language we could not also express using first order logic over words, right? So we used MSO here, but like the second order, monadic second order logic, but this could not be expressed. I mean, we did not prove it formally, but like we had enough intuition to show that like this could not be expressed using first order logic. Okay, and then I also mentioned about this theorem called Kamp's theorem, which you can try to see what it takes. And then we started this proof that indeed every LTL definable language is non-counting. And how do you do the proof? Using the structural induction on LTL formulas, right? So you start with phi being the phi formula phi is true, then it's an atomic proposition P. If it's a disjunction of two LTL formulas, then if it's a negation of phi is a negation, phi is a negation of psi, then you have the next of psi and so on. And we stopped here. So we proved all these cases. And we said that today we will look at this particular case, the proof where you have phi 1 until phi 2, right? So for the other cases, I think we were just doing the if and only if they were quite not too difficult to sort of see. You can just do the if and only if directly for all the other cases. Here we will just, it's a little more complex for this particular case, phi 1 until phi 2. What we'll do is like we'll look at the two directions separately, right? So first we'll try to show that indeed if UVN x belongs to L of phi, then this implies that UVN plus 1x belongs to L of phi, right? So this direction first we'll try to see. So suppose you have that UVN x belongs to L of phi, right? Then what do we know? We know that there exists some j, index j, such that UVN x starting from this j, it satisfies phi 2. And for all k less than j, we have that the suffix starting from k, it satisfies phi 1. This is just from the semantics of ATL, right? In order to prove this statement now, we will consider two cases. One, where j is less than equal to u plus v. So essentially, it looks like the following. So if I look at this kind of a timeline, so you have u followed by like these several v's. So just to say that essentially it's like this point is the same as this point for the sake of the proof, so that it is easier to visualize. I put a gap, like you have from here, you have a v, then another n minus 1 such v's, vn, and here you have like from here you have n plus 1 such v's, right? I just put a gap here just to align things, but essentially this point is the same as this point. Okay. Now, if you have, let's say, that the j is here, j is less than equal to u plus v. What is the j? Is that from this suffix you satisfy the phi 2. Okay. Now you see that if this is the case, so we are trying to prove this direction, right? So we already have that u v and x belongs to L phi. And so here, right? So here, this particular suffix, this infinite string, it indeed satisfies phi 2. Okay. What we would like to prove is that now this suffix also satisfies phi 2. Why this is true? Just by structural induction. Okay. So essentially, by induction hypothesis, we have that if this is x j, it satisfies phi 2, then u v n x sorry, u v n plus 1 x j this, okay, this also satisfies phi 2. Okay, is it okay? Right? So this is just by the induction hypothesis. And now, again by induction hypothesis, we can see that all these places, so all these places here, they satisfy phi 1. Okay, so suppose you consider a point here. Suppose you consider a point here which satisfies this phi 1 here, right? Now, exactly by the induction hypothesis, again you can show that this point here also, so you have an additional v, they will also satisfy phi 1, right? So this is clear enough. So all this, so from this point satisfies phi 2. This by induction hypothesis, I have this satisfies phi 2. Everything here, like all the points, everything here, they are satisfying phi 1, and by induction hypothesis, these also satisfy all these points, they also satisfy phi 1, right? And then here you have this is satisfying phi 2. Hence, we have that, particularly if you look at the starting point, it satisfies phi 1 until phi 2, right? If I look at the starting point here, this satisfies phi 1 up to here and then satisfying phi 2 from here. So this point satisfies phi 1 until phi 2, right? Hence, what do we have? We have that u v n x, it u v n plus 1 x, this belongs to L of phi, where phi is phi 1 until phi 2. Clear? So what about the online participants? Any question?
No. Makes sense.
Okay, good. Thanks. So now we have the other case, which is like j, if j is greater than u plus v. Okay, so you have the j somewhere here. I mean, the u plus v, it's like here. So the j is somewhere beyond this point, right? The j is beyond this point. So suppose I'm just saying that the j is some point here. Okay. Now, in the other string that we are having, we have an extraction. So I write it like this. Okay. Again, I'm just, so this point is the same as this point. I'm just aligning them. Now you see that starting from here, everything is the same, right? Starting from here, everything is the same. So if this point satisfies phi 2, then this point will also satisfy phi 2. And again, for all these points, if these are satisfying phi 1, so essentially the suffix starting from here, the entire infinite suffix starting from here, this satisfies phi 1, right? Similarly, this satisfies phi 1. All these points are satisfying phi 1. We just have these, all these points are also they are satisfying phi 1. Okay. Now, what about something like here? All these things, like if you consider a point here, okay, some k which is let's say less than equal to u, if you consider such a point, right? So they satisfy this phi 1, and then again by induction hypothesis you have that, like from here with that extra v also, this point here, right, it will also satisfy phi 1, correct? Okay, so all these points here they are satisfying phi 1, all these points here they are satisfying phi 1. And what else, like what about some point here, right? So I have to show that these points here also, right? These points here also, they satisfy phi 1. How do I show, how do you show this? Take the first V block. Take the first BV block here, right? So you have one less V here, and if you consider exactly some point here, you have one extra V, and then again by induction hypothesis, you can say that these points will also satisfy that the phi 1. Okay? Okay. So if that is clear enough, then again we have that UVN plus 1x satisfies phi, right? Where phi is phi 1 and phi 2, right? Clear? Right? Is it okay? Right? All these things. Okay. So I'm not writing in detail, but I think from the diagram it's clear enough. Now, so Vishal, this was also fine. This part.
Yeah, so we are just considering like with every point in this u, v, and plus 1x and seeing whether or not it will be satisfied. And it's, yeah, makes sense.
Yeah. So essentially, I'm saying that this string satisfies phi, this whole string satisfies phi, and I'm trying to show that this whole string also satisfies phi, like starting from the beginning. So so what do we want to do? Because this point satisfies phi 2, here we have to show that like every point before this point, before the j, right? All these points, they are also satisfying. I mean, it's like j plus v here, actually, this point, because of the additional v. Okay, but since we look at the future starting from j here and the future starting from j plus v here are the same. So of course, if here you have this satisfies phi 2, this suffix, then this suffix will also satisfy phi 2, and every point before that here satisfies phi 1, and we want to show that every point here they also satisfy, yeah, each point here also satisfies phi 1, right? And this we are proving by that induction hypothesis. Okay, and for that we said like this part is exactly the same as this part, so there is nothing to, like, it's nothing to say here, like it's everything is the same. Now for this part, I mean for this part we are doing the using the induction hypothesis, right? For this part, because you have an additional v here, and for this part again you are also using an induction hypothesis from this side. Clear? So that's what we did with the phi 1.
Yeah, makes sense. Yeah.
Okay, because for choosing this part, you have, like, if you consider a point here and the consider a point here, there is an additional v you have here, an extra v, right? An extra v here you have, and that, so essentially if you are if let's say a point here k starting from like u v n x k, this satisfies phi 1, then in UVN X n plus 1 xk, which is a point here, right? This also will satisfy phi 1 by induction hypothesis, right? So this is what we are saying. Okay. Similarly for points here also. So it's by the induction hypothesis, right? So now every point here satisfies phi 1, and you have this point j plus v here, which satisfies phi 2. Hence, from the beginning, you have that it satisfies phi 1 until phi 5. Okay, so we are done with one direction. What is the direction? That if uvn belongs to L of phi, then uvn plus 1x belongs to L of phi. Now we'll prove the converse direction, which is that if uvn plus 1x belongs to L of phi, then uvn x belongs to L of phi. Okay. So we want to prove the converse direction. So suppose we have that uvn plus 1x belongs to L of phi. So then what happens? Again, by the semantics of LTL, you have a j such that this from this point, the suffix, it satisfies phi 2. And for every point before that, you are satisfying phi 1. Now again, just like the previous one, we are considering two cases where j is less than equal to u plus v. Okay, so this is this particular case, j is less than equal to u plus v. So what happens? Like, so suppose uh, you have like, so if this from here, if you are satisfying phi 2, then from here also you would satisfy phi 2 by the induction hypothesis. You just remove one v, right? So if you have, let's say, u v, strictly speaking, this is yeah, sorry. Okay, so if you have u v n plus 1 x j, so this is the suffix. If this satisfies phi 2, then by induction hypothesis, we have u vn x j, right? So this also satisfies phi 2, right? And similarly for exactly by the same reasoning, if all these positions are satisfying phi 1, then these positions here also will be satisfying phi 1, exactly by the induction hypothesis, right? So starting from the beginning, you have this satisfies phi 1 until phi 2, and hence we get this also satisfies phi 1 until phi 2, right? So we proved for this case that u vn x satisfies phi 1 until phi 2. Okay. Now, what about the other case? Again, suppose you have j is greater than u plus v. If j is greater than u plus v, so now you have here j, and here you have j minus v, right? So this one v is missing, you have j minus v. Now, here you have like this suffix satisfies phi 2, this suffix will also satisfy phi 2, and everything here satisfying phi 1, everything here will also satisfy phi 1. So the only part is this thing. The only part is this thing. Now, again, it's by the induction hypothesis, right? So for all these points, you have an extra v. Here you don't have the extra v. By the induction hypothesis, you have that. From here, you satisfy that phi 1. Here also, you will be satisfying the phi 1 by the induction hypothesis. Hence, we get that u vn x also belongs to L of phi. Okay, so we did the proof in both the directions. Clear? So this is this. Let's see a couple of more examples. Uh, so suppose consider this set of atomic propositions, just P, and now the language L is such that P occurs in all even places, right? So if you recall that how did our letter, how did the alphabet look like? How so if AP is the set of atomic propositions is this. So what is our alphabet? Phi n. Good. So our alphabet sigma is here, the empty set, and Okay. So, so now we are saying P occurs in all even places. In the odd places, you may have P or you may not have, right? So how we learn? So you can clearly draw an NBW for this, right? I mean, it's just very simple. You have something like this, and here you will have, let's say, I think I should carefully. Okay, and then you have the even places you should have. Correct? Now, is this a non-counting language? Is this a non-counting language?
It is not a non.
It is not a non-counting language. Why do you think so?
Because if you take UV or N naught, and then you take V as P, then you can kind of say the N plus one will have P at the odd position. Oh wait, we just want it. If we take V as phi, then we can get phi in the even position. Yeah.
Sorry, so what are you saying? Maybe you can say.
If you take V as phi,
So I have, so this is the thing, right? I have U, V, and X belongs to L of phi if and only if U, V, n plus 1 X belongs to L of phi, and these are for, so the quantification is very important, right? So it is like there exists some n0 such that for all n greater than equal to n0 and for all U, V belonging to sigma star and X belongs to sigma omega, right? This is the thing.
yeah. So now if you take, you can write this as UV N naught, and then V bar and X. So if you take V as phi,
Okay.
then you'll for M is equal to 0, this will satisfy. But then for M is equal to 1, you can place or M is equal to 1 or 2 based on the parity of N naught. We can place phi in the even position.
So you were saying it is non-counting.
It is not.
It is not non-counting. Okay, it is not non-counting. So what is your V?
Phi.
V equal to the empty set. Okay. So then what is the language that you are talking about? What is your U? U is empty.
Anything.
Okay. So you are saying then phi raised to some n0, some n.
Yeah. So if suppose
that n should be.
it depends on the parity of N naught.
Mm-hmm.
So suppose you N naught is even,
Okay.
then you will have a word U V power N naught X. Oh wait. Pi is itself not.
It is not in
It is not there.
it is not in the language, right?
Yeah.
Because in the language you want P to occur in all even places.
Right.
But suppose we have a word like this where phi is correctly in a odd position, and now if we raise it to any even power which is larger than n naught, then everything just gets shifted to the other parity afterward. And
Yeah, I think you are almost right. So how should a word look like? I mean, suppose I say that, suppose I say something like this, that I have the P, okay, and P is appearing, let's say some n times, where n is even and n is greater than some n0. Okay, so suppose, let's say I have P appearing some even number of times, 2n0 times, and I say after this, suppose I say phi dot p omega, right? Phi dot p is like, so you have p some number of times, like some n 2n0 number of times, right? P 2n0 number of times, and then you have like a phi followed by a p, by a p. So this is in the language. Clear? This is in the language L of this language L, right? So this language L, P occurs in all the even places, correct? And what is my V here? My V here is just a P, let's say, okay? And now, if I say that consider this P 2n0 plus 1, so I'm repeating the P now odd many number of times, and then I have the phi dot P omega, right? This does not belong to L, because now I'm starting to have the phi as well as the last P here. These are in the odd positions, right? Hence, this is not non-counting. Okay? Is it okay? So for the online participants, is it clear?
Yeah. Makes sense.
Okay, good. Now, here we had, so I make a slight change in the example. So here you had both P, I mean P in the even position, but in the odd position you could have either P or the LT. So now I make a little change, which is like you have now phi dot P omega, right? Whole omega. So now it's, the automaton will look very similar to what we had. I have phi and I have a P here. Right? So this is phi dot P omega. Earlier, I also had a possible P here as well. Right? So this I do. Now, what about this one?
This is non-counting.
This is non-counting.
Yeah.
Okay. And
we can give a formula. We can say globally phi and next P and P and next.
so first you will say phi because it starts with a phi.
Yes.
And then globally, phi implies
Next.
P. And I can put the end here. And P implies next phi. Okay. So actually it's like the way I should write it is like not P implies 1 and P implies X of not P. Okay. Sorry, I think yes. Okay. And here also say not P. Okay. Okay. Okay, this is fine. Okay. So indeed, you can actually write an LTL formula for this, but you can also try to like look at all the different possible U's and V's, and for everything you can argue that it's indeed non-counting. Okay, so this kind of ends our current discussion on LTL, linear temporal logic, which is like a linear time we were talking about, right? Time is linear. So you're just looking at how the system evolves over time, which is a linear time. And now we are going to talk about another kind of temporal logic where time is kind of branching. So it's a branching temporal logic, it's called. So this particular logic that we'll be looking at, it's called the computational tree logic. Okay. And this was proposed by Clark and Emerson and also by Joseph Tsouplakis. So it was in 1981. So LTL was slightly earlier, like it was in 77 by Amir Newell, and this was in 81. Okay. And now when we were talking about LTL, you can think of like there are different possible paths, and it's like a state satisfies this formula phi. Intuitively, it is like for all computations, you satisfy the formula phi. So it's like when I say for all computations, it's like for all possible paths, it satisfies phi, right? So you say that so you choose the path and then you just like looking at that path only, like it's evolving linearly. Now, suppose if I tell you something like this, for every computation, it is always possible to return to the initial state. Okay. For every computation, it is always possible to return to the initial state. Okay. So the initial state I write here begin. Okay. Now, just think about this, that if I have a computation here, which goes here and then it stays here, right? So it is always possible that even if the computation is staying here, it is always possible to, from here at any point, it can actually take this transition and then it can reach here. Correct? So the intuitive meaning, like for every computation, it is always possible to return to the initial state. This is indeed true here, right? It's indeed true in this system. But now in LTL, if I have to sort of write this, okay? So how would you like to write this in LTL? What is the natural thing you would like to write? For every computation, so it is always possible to reach the initial state, right? To reach the initial state. So I'm saying that you have the computation and you are saying that it's possible to reach the initial state. So what is the way you would like to write it in LTL? Like the most sort of intuitive thing that comes to us.
Like or over every initial state, like P, and P implies like globally, eventually P.
So suppose I just have a single initial state, let's say, then you are right, but then just to simplify things, what would you like to write?
So let's the initial state, let's say P, and its P implies globally, eventually we'll get P. So
So you are saying P implies
G
globally eventually P.
P.
Okay. So here, okay. So here I'm just writing instead of the P because I wrote the P here for the other state. So let's say I say begin, it's a proposition, is GF begin. Okay. So if you are, so what does it mean? Like if you are currently in begin, it implies globally. So you don't put a globally outside. You are just saying this thing. If you are in begin, then eventually globally, I mean, so then globally eventually, infinitely often you will see begin, right? But this is as good as saying only this much. Globally eventually begin. Why? Because to start with, you are anyway in begin. This is always true. This is my interpretation. Okay.
Okay. Yeah.
Okay. So now globally eventually begin. Okay. But now I will say that though my intended semantics, intended meaning of this is true here, that for every computation, it is always possible, right? Wherever I am, I can always reach the initial state. This, in fact, doesn't hold true in this particular transition system or the Kripke structure. Why? Because you can have a path which just starts from here, it goes here, and it just always stays here, right? You have this begin followed by P omega, correct? This does not satisfy this infinitely often begin. GF begin is infinitely often begin. This computation does not satisfy, right?
We say something like begin implies next P and P implies globally eventually P. The P state.
So what are you saying?
If we are in begin, then next we shall go to P. So begin implies next P.
Yeah. So you are saying begin implies next P
And
P implies
globally eventually.
P implies globally eventually P. But this is also fine
Begin.
because I can say globally eventually P. Begin implies next P, so you come here, and then you are always here. So that is.
Yeah. So this will satisfy
This will satisfy what?
the.
No, I'm saying that if I consider a run, which just comes here and then this begin P omega run,
Yeah.
it satisfies this.
Yeah.
It satisfies this. But it does not satisfy this particular property, is what I'm trying to say.
Okay. Okay.
What I'm trying to say is that indeed such a property we may not be able to express using LTL. Okay, you need something else. But it turns out, which we will not see today, but maybe sometime later, that indeed this CTL and LTL are incomparable. So there are properties which you can express in CTL, but not in LTL, and vice versa. Okay, so there can be certain properties which you can express in LTL, but not in CTL. Okay, so yeah. Now, what is this branching time? At each point, this logic is going to consider that there may be several possible successors. Okay, so there may be several different possible futures. So this is what this logic will kind of try to consider. Okay, so it will have something called path quantifiers. Okay, so the idea of the path quantifiers is like you can have multiple possible paths, right? It will say that for all paths starting from this state, it will have such quantifiers, or it can have quantifiers which are of the form there exists a path in which something will hold. Okay, so these kind of things we'll see. So essentially this is for all computations or for all paths, so we will exactly use this universal quantification, and we also there exists a computation or there exists a path which is for which we will use this existential quantifier, right? We will use this symbol. So now if I say for every computation it is always possible to reach the initial state, I'll put it like this. For all paths or for all computations, this is what it says, for every computation, it is always, so globally, for always, there exists a path. Okay, now you see that even if I'm here, I'm just looping here, from every such state, there exists a path. That is what it says. There exists a path. There exists a path such that eventually I will go to begin. Okay, so it is always possible to reach the initial state. Okay, so this kind of captures the intended meaning. So these are just a few notes. We'll look at them, these things, each of these things in more detail later. So this comparison, if you compare this logic with LTL, so one thing you will note is that the expressiveness, it differs. Okay, it's not like the one is stronger than the other. One is more expressive than the other. It's not like that, but they are incomparable. And the model checking algorithms and their complexities, they are also going to be different. Okay, in fact, we are going to see that model checking CTL is much complexity wise, it's much simpler. Like you have polynomial time complexity. Whereas this was polynomial space, it was space complete for LTL, right? Uh, and then when you talk about two different formulas in LTL or CTL, so how do you like if I say that these two formulas, which may not syntactically look the same. So you have a formula phi and a phi prime, which are in LTL. Now I'm asking you the question that how do you prove that these two are actually equivalent? Or, I mean, proving is one thing. I mean, you can try to get it into some canonical form, etc. But what is what is one way to see that they are equivalent? One thing is like if the language of phi is the same as the language of phi prime, right? The set of words, or it's the same as saying like this also we use words of phi is the same as words of phi prime, right? So if this is the same thing, then we will be saying that these two formulas are indeed equivalent, right? When we say that these words, essentially it means like it's kind of a like a language equivalence, right? It's a language equivalence. Now, language equivalence is not the only form of equivalence. There can be other kinds of equivalence over, let's say you are given two transition systems, and then you say that this is the language of this transition system, this is the language of this transition system. These two transition systems are equivalent, or these two automata are equivalent if their languages are the same. This is one way of proving equivalence, or one notion of equivalence. There can be other notions of equivalence also, right? Which we'll see. And one such equivalence is a bisimulation equivalence, okay? Which is a stronger notion. When I say it's a stronger notion than language or trace equivalence, I mean, language equivalence is often also called a trace equivalence. A trace is like a computation, okay? The set of computations of the two systems are the same, so they are trace equivalent. And bisimulation is stronger. When I say stronger, what does it mean? What does it mean?
That the two things which are equivalent by traces need not be equivalent by simulation. But if they're equivalent by simulation, they are
Exactly.
definite.
Okay, so that's what the being stronger it means, that if they're bisimulation equivalent, then they are trace equivalent as well, but not the other way around. Okay, so bisimulation equivalence, it's a stronger notion. Okay, so this is something we'll see. Okay, and for CTL formulas, when we are going to talk about notions of equivalence, so these are more relevant. Okay, so what is a pre-order? Do you remember what is a pre-order? What is a pre-order or a quasi-order? What is a pre-order or a quasi-order? Reflexive and?
Transitive.
Sorry?
Transitive, reflexive.
Reflexive and transitive, very good. So you have reflexive and transitive. Okay, so this is called a pre-order or a quasi-order. What is a partial order? What is a partial order?
It will be anti-symmetric also.
It is also antisymmetric, right? So if you add reflexive, transitive, and antisymmetric, then it's called a partial order. These things should be on your fingertips. Okay, what is an equivalence relation? Reflexive, transitive, symmetric. Okay, so these things you should never forget. Okay, so it's a partial order, it's reflexive, transitive, antisymmetric. it's reflexive and transitive. This is called a pre-order possible. Okay. So now language language equivalence, it's some kind of, it's a pre-order, right? Sorry, not language, I mean uh, language inclusion, for example, right? It's a pre-order, and a simulation relation is also, it's a pre-order. Okay, it's like one transition system can simulate the other transition system. So if it can simulate the other transition system, then then it also includes the language of this one. Okay, so if, for example, a transition system, let's say K1 simulates K2, right? If this is the relation between the two transition systems, then it's like L of K1 and L of K2 are related this way, that L of K2 is a subset of L of K1. Okay. So this is, yeah. Okay. So this one. Okay. So now let's come to the syntax of CTL. Okay. So we will be looking at each of these things in more detail, like how the expressiveness it differs, what is the model checking algorithm for CTL, what is its complexity, then for LTL, for CTL, in the context of CTL, we look at simulation by simulation, etc. Good. Now, for the CTL syntax, we have like a true, we have this proposition A. A belongs to the set of atomic propositions, right? A belongs to AP. Then we have phi1 until phi1 and phi2 conjunction. And we have a negation of phi. We have exists of psi for all psi. Okay. So what is this? You have in the CTL syntax, you start with a state formula. So you have the state, and you are saying that in this state, I'm going to satisfy a CTL formula. Okay. And the state formula and the path formula, they are going to alternate. Okay. This is like a path quantifier. So you are saying that in this state, there exists a path such that in that path, some path formula is going to be satisfied. Or in this state, for all the paths that you have starting from this state, in each of these paths, some path formula is going to be satisfied. And how does the path formula, how do the path formulas look like? They're exactly like the way you have seen in LTL. Okay. But with a small twist, which is like, okay, now you have x of phi. In the next state, phi should hold. So this phi now becomes a state formula. In the next state, phi should hold. Now phi is a state formula. So you see that the state and the path formula, they are alternating. Or you are saying phi1 in the start, in this path, phi1 until phi2 should hold. So at some point of time, at some state in this path, phi2 should hold. And in all the states until then, okay, before that, phi1 should hold. So this is a path formula. Okay, so you have state and path formulas, they are alternating. Okay, and so suppose if I have the set of atomic propositions, if it's of this form, x equal to 3x greater than 1, right? So these are my two atomic propositions, let's say. So if I have, there exists a path such that in the next state, this state formula has to hold true. This is a valid CTL formula. Okay, so this is, when I say a valid CTL formula, here I am saying it's a valid CTL state formula. From this current state, there exists a path such that in that path, in the next state, this state formula should hold. Okay, this is, the whole thing is a state formula. This part is a path formula, and again, this thing is a state formula. Now, if I say that there exists a path, okay, such that x equal to 1, right? So I'm expecting now there exists a path In that path, I'm expecting a path formula, right? But instead, I'm getting a state formula here. Okay. And similarly, there exists a path such that again there I'm getting a for all here, right? If I had, there exists a path and then this part is like if there is a next here, next. This could have been fine for this part, right? But this is not good. So it is not a valid CTL form. Okay.
So if earlier we had there exists and next after that, then it still works, right?
So you are saying, suppose if I have just something like this, there
same.
exists a path such that next
And the whole thing.
x equal to 3.
Better.
Okay. So this is valid, right?
Yeah.
Because what I'm saying that there exists a path. So this whole thing is a state formula. In that path, in the next state, you have this state formula which should go. Okay, these are valid formula. Now let's look at, for example, these derived operators. Like we had also eventually, right? We saw in LTL. Similarly, we can also have this. So there exists eventually phi. There exists a path in which eventually I'm going to see phi. So it's like saying there exists a path in which true until phi. For all paths eventually phi. For all paths true until phi. There exists a path globally phi. Okay. There exists a path globally phi. Now you can try to write this using the eventuality, like we saw globally and eventuality you can negate and write, right? So how can you write this?
Not eventually, no. There is.
So you have there exists a path.
There exists, not eventually.
Okay, so you are saying there exists a path, not eventually, not phi. Okay. Now I claim that this is not a valid CTL formula. Why? I mean, the reason being, see, the negation is applied on the state formula.
State.
Okay, so here we are not allowing the negation to be applied on the path formula. You are right. I mean, essentially, semantically, like what you have in mind, it's fine. You are actually like, I mean, it's, to think, if I want to interpret it, it's there is no, that way there is nothing wrong here. You are saying there exists a path such that in that path, this thing doesn't hold. I mean, this if eventually not phi doesn't hold. So essentially, it will be like a global phi. So it makes sense. But syntactically, it does not allow. So what can you say?
There exists phi until false.
We can
We don't
pull
have
the
to-
first negation out, yes.
Sorry?
We can just pull the first negation out somehow and change with for all
Okay, right.
actually, because this is at the state formula level.
Okay. So I can say negation of, it is not the case that along all paths, what?
Then the same, eventually
Not phi.
not phi.
Okay, good. What about now the for all globally phi? Can I use this eventually here again? Along all paths globally phi. What can I write?
Not there exists.
It is not the case that there exists a path
Where eventually.
where eventually not phi. Okay, good. So now there are some people would, I mean, it's just sometimes people use such things called there exists a path such that globally always phi. It's like potentially always phi. It means that there exists a path, it's always phi. For all paths, always phi. It's like invariantly phi, right? Invariantly phi. It's an invariant which should always hold true, correct? So it's invariant. Good. So now we'll look at some properties. Suppose I say mutual exclusion. Okay. So what can you write? I mean, you can use for all globally, eventually, whatever you want. So how can I write now? We have seen this in LTL.
Globally, phi one is phi one.
So we use something like this, right? Critical, let's say 2 processes. We had the crit 1 and crit 2. We used something like this. So using this, how can you write?
Globally crit 1 and not crit 2, or crit not crit 1 and crit 2.
But it can also happen that none of them is there in the critical section, which is also fine. So what can you write?
So then, or not crit 1 and not crit 2.
Not crit 1 or not crit 2. What else?
Oh, wait. So we can just say it's not the full stack.
So globally not of crit 1 and crit 2.
Globally not of crit 1 or crit 2. So you want to hold these at the initial state of the case structure, right? But this is not a state formula. You have to write a state formula. It's not a state formula. Whatever you have said, it's like an LTL formula, but in the context of CTL, you want to write a state formula. The globally is a path operator. In that path, it is always. So what you do, right? You just add an overall. For every computation, starting with its initial state, for every computation, it is always the case, right? So you can have computations which can look like the following. You can have these, there can be some branching like this, right? So again, some branching and some branching. You want that for every such possible computations. So one computation is like going along this branch. Another computation can be this branch. Another one can be like this one. For all such computations, you want that you should not have, I mean, you should have mutual exclusion. Okay. So for all paths, starting from here, for all paths, it is always the case that both of the processes should not be in their critical section at the same time. Okay. So this one we kind of saw, the second one, right? Phi is true infinitely often among all paths. How would you write this? Phi is true infinitely often among all paths.
For all paths,
For all
globally,
paths.
eventually, no,
Globally for all.
Okay. For
yeah.
okay. So it's just, I mean, you have the right intuition, given that you have seen LTL, you also understand, like, I mean, you have the picture in mind. It's just that you have to get a bit familiar or used to a syntax. That's all. Okay. For all, globally, for all, eventually. Okay. So, I mean, if I want to write this, each process has access to the critical section infinitely often. How would you write this? How would you write this?
For all globally, for all eventually. Crit 1.
Okay.
And
Distinction. Sorry. Yeah, it should be conjunction. Thanks.
So there exists eventually is not sufficient here, is it?
Well, when I say that has access, it's like for every computation, it intuitively means that whatever be the computation, it is always the case. Whatever be the computation, if you just say there exists, then it's like there is a possible such computation. It doesn't say that it is always the case. I mean, for all possible computations, it's the case.
Okay, so access means in every such.
When I say each process has access to the critical section infinitely often, it means that for every possible computations, always it's the case. It's similar to LTL, right? When I say in LTL that something holds true, for all possible computations, it holds true. Okay.
Makes sense.
Process has access to the critical section. no matter what, like infinitely often. For all possible computations, each process has access to the critical section. Okay. So when I say that, if I say that there is a possibility, when I say that there is a possibility, then you have intuitively like there is a existential quantifier. There is a possible such computation. Does it make sense?
Yeah, got it. Makes sense.
Okay. Now, what about this one? Each red light phase is preceded by a yellow phase. Again, for all computations, always the case. Okay, whenever you have red, for all computations, always, whenever you have red, it should be preceded by a yellow.
So that
So
means
for all
not
globally, not
So first, let me write the for all and the globally. This part is okay. Yeah. Then
for all, if, oh wait. Not of there exists, there does not exist a path such that not yellow implies red.
sorry. Okay, go ahead.
Not there exists.
So you are saying that I don't. This is inside this
Yeah,
part.
inside.
Okay. For all globally, not there exists a
There
path.
exists a path such that not yellow and next red. Oh wait, do I have next?
Yeah, we can just replace that with a for all and
Sure.
So what are you saying? Not yellow.
Not yellow implies next red.
or you can say not yellow until
Implies X red.
No,
This I don't.
we want it to be preceded, so will it be until only? No. We can say
until.
until.
But
Do we want it immediately preceded by
Yeah.
yellow? So then next red.
Yeah, I want it to be immediate. So if I have like a red, so wherever there is a red, right? So if I want, so let's say I have something, okay, so if I have the red here, then I should have the yellow here. Okay, if I have a red here, I should have the yellow here. If I have a red, yeah, I mean, I can have, for example, a yellow here, but there can be another yellow here. This is fine, right? It says that the red should be preceded by a yellow.
So this is saying like for all the paths,
Hmm.
globally there does not exist a state. State implies continuing.
So what does it say?
none of the
So
states.
what does it say? So it says that
For none of the states there exists a path.
so if you see a red, then there should be this
Preceding yellow.
preceding yellow. Okay. So and
so I guess we can say it like this in
so
some.
if you have, let's say, if you don't have the red, okay, so whenever I see each red light is preceded by each red light phase is preceded. So whenever I see a red, there has to be a yellow. Okay, and
sort of implication it should be and, right? Like
no, if it is not a yellow, then the next cannot also be red.
yeah.
Okay, so this is, I think, so if I say all paths globally, if I have not yellow, then it implies
Not red.
that
Right.
next
Not red.
X is not red.
Hmm.
Okay. So let's see if the syntax is correct. So for all globally, this is a state formula, not yellow, implies X not red. So here also I have
For all X, I guess.
yeah, I'll say indeed. For all paths, okay, for all paths, it is not the case that for all my successors, it should not be the case that they are. So if I am not yellow, then for all my successors, it should not be the case. I mean, for all my successors, it should be the case that they are not red. Okay, they are not red because each red should be preceded by a yellow. So if I'm not yellow, then for all the successors, they should not be red. Okay, right? So here we have the formula. So either you say you could have also written as yellow or right. So the implication you could have written as a differential. Clear? Okay, are we convinced with this? Okay. How about every request will eventually be granted again? Along all computations, it is always the case that whenever there is a request, there should eventually be a grant. Right? Yeah. Saying for all paths, globally, request implies for all paths.
Globally for all eventually. Wait, we need eventually. For all paths eventually.
Okay. It is always the case. For all paths, it's always the case. Whenever I'm seeing a request, right, it should eventually be granted. So whenever if I'm seeing a request here, it should eventually be granted. It should eventually be granted. Whatever computation you take, it should eventually be granted. Okay. Yes. So let's look at the semantics of CTL. So we looked at the critical structure is given like this. You have the set of words, atomic propositions, set of initial words, then this R, right? R gives the transition relation among the words. L is a labeling function, right? And suppose you have S, S is a word or a state, let's say, okay, W. And these are CTL state formula and psi is a CTL path formula. So how is the semantics defined? I mean, we already understand it now, but just for the sake of completion. So S satisfies A if and only if A belongs to the set of labels of, the set of labels of the set of atomic propositions which are true in, correct? S satisfies negation of phi if and only if it is not the case that S satisfies phi. Okay, we could have also written, we often write it like this. It is not the case that S satisfies phi. S satisfies the state formula, there exists psi, right? All these formulas here, these are all state formulas, right? We are talking about a state. A state satisfies a state formula, path satisfies a path formula. S satisfies exists psi, there exists a path starting from S, if and only if there exists a path pi belonging to paths of S. Paths of S is the set of paths which start from S, and pi satisfies psi, right? Psi is a path formula. S satisfies for all psi. If for all paths pi starting from S, we have that pi satisfies psi. For path pi and path formula psi, we have pi satisfies x of phi, right? So this is a path formula. X of phi is a path formula. So phi has to be a state formula, right? If from the next state in that path, it satisfies phi, right? Next, phi 1 until phi 2, this path satisfies phi 1 until phi 2. Exactly, we saw that this in LTL. If there exists a position j which satisfies phi 2, and for all other positions until j, you have that it satisfies phi 1. Good. So here there was some illustrative examples in that book. So we are following this book, right? Principles of Model Checking by Catovan. So if you have there exists, so you remember that like this is the same as f, right? It's the eventuality. In some places they write the diamond, and the box is the same as what? Globally, yes. Okay. So here it says there exists a path such that eventually black. Indeed, there exists a path such that eventually black. There exists more than one path. There exists a path such that always black. Such a path exists. For all paths, eventually black. For all paths, like you go here, you go here, you go here, you go here already, right? For all paths, eventually black. For all paths, it's always the case that you have black. So it's just right. So this for all paths globally black is the same as, or always black is the same as G black in LTL. For all paths, always black is just the same as always black in LTL. There exists a path such that gray until black. Indeed, gray until black. Correct? Even this one also. Gray, you start with gray and you have a black. For all paths, gray until black. So wherever you go, gray until black. So here you have gray until black. Good. And some simplifications, you can do an existential normal form in the sense that you can allow negation and you can get rid of the universal quantifier. Okay. So yeah, also we don't allow disjunction because using De Morgan's law, you can remove the disjunction and have conjunctions. So for each CTL formula, there exists an equivalent formula in existential normal form. So what is the thing? Then you have to remove this for all x and for all until, right? For all x, it's not the case that there exists a path for all paths. For all paths, the immediate successor satisfy phi. It's not the case that there exists a path such that the immediate successor satisfies negation phi. Okay, so simple enough. And then we have for all paths phi 1 until phi 2. Again, it's not the case that there exists a path in which the negation of phi 1 until phi 2, right? So it's like not of phi 2 until not of phi 1 and not of phi 2. So this is something that you want to hold, as well as it's the case that there should not exist a path in which it is always the case that you have negation of phi 2. Okay. Okay. Right. So okay, this is clear. This semantics. Any question? Okay. Then similarly for these ones also, for derived operators too, we can remove the for all path quantifier here. If you have for all eventually phi, for all paths eventually phi, it's not the case that there exists a path such that globally always negation of phi. For all paths always phi, it's not the case that there exists a path in which eventually negation is 5. Okay, so in fact, like just you can, so this is something we already saw. If you have, let's say, this kind of things, you can again have like, so this conjunction negation over this, it becomes a conjunction, it becomes a disjunction, and you can put the like for each of the uh, eventuality operators, you can replace them with a global end of it. So it's just simple thing. And then, yeah, as we stated that you don't have the disjunction, and we are just using with the conjunction, which suffices. And as we saw in LTL, we saw there were positive normal forms. You can also think of positive normal form in CTL, right? So what was the idea of the positive normal form?
Like we
Like
push the negations.
Push the
into
negations.
the,
Atomic propositions. Yeah, right. So you push the negation inside until the atomic proposition. So you have the negation only over the atomic proposition, right? So again, for each CTL formula, there exists an equivalent formula in PMF. So there is one thing I should maybe add here, that whenever you are doing this translation, right, from a given CTL formula, which we started with, to this ENF, you see that here, again, this phi2 is appearing multiple times, more than once. So it can again blow up the size by an exponential factor, right? And similarly for the PNF also. So you are pushing things inside, negation of phi1 or negation of phi2, not true is false, not of not phi is phi, negation of phi1 and phi2 is negation of phi1 or negation of phi2, not of for all x phi's there exists a path such that next not phi. Similarly, not of exists x phi's like for all paths next not of phi, right? Not of exists x phi is for all paths there exists. So for all paths uh, in the next state, you have negation of phi. And similarly, again, you have negation of for all paths. It's not the case that for all paths you have phi1 and phi2. Okay, so that means there exists a path such that this phi1 until phi2 is violated, right? So it's like phi1 and not phi2, weak until not phi and not phi2, right? So we saw these things. Similarly, it's not the case that there exists a path such that phi1 until phi2. That means for all paths, you have phi1 and not phi2, weak until not phi1 and not phi2, right? So you remember the difference between strong until and weak until. Yeah, that this can continue to hold forever in a weak until, right? And whereas in strong until, this, if you have phi1 until phi2, then phi1, then phi2 has to hold some, which is relaxed with the weak until. Right. So here also we see that there is an exponential blow up when translating the CTA into positive unit form. And here also just we had a release operator as we saw in LTL. You can also use a release operator, right? So this is how the release operator. So if you have there exists phi1 or phi2, it's like saying now it's not the case that for all paths you have not phi until not phi2, right? So when you had, like, if you had LTL, then you would not have this for all thing. Rest remains the same, right? You had just not of negation phi1 and
So
so.
should there be for all eventually not phi?
For all eventually, why?
Because it's not at the first step. At eventually also we don't want that happening. That's the right.
So there exists a path in which phi1 release phi2, right? So it's like you are saying that the phi2 continues to happen. It will continue to happen until that point where phi1 happens.
Yeah. So that shouldn't we say it's eventually not going to happen? We are currently at a different stage.
I mean, we are currently at some state. We are at some state, right?
Yeah.
And we are saying that there exists some path where you have like.
So now we are saying it's not the case that for all the paths,
Yeah.
eventually it does not happen like it happens like that, right?
No, what I mean, the until essentially takes care of the. So if you talk
Oh,
about the until, the until takes care of the
Yeah,
right, because
I saw it
eventually
wrong.
like true until, right? So you have an until here. You have an until.
Yeah.
Okay, and similarly, if you say for all paths phi 1 release phi 2, then you can say that it's not the case that there exists a path in which negation phi 1. Okay, so how much time do we have? So maybe I'll just sort of say a bit and I'll try to finish today. So in the CTL model checking, what we are given, again, we are given a formula phi and we are given a Fouquet structure. And the idea is the following, that we compute the set of states which satisfies phi. Okay, the set of states that is, I mean, the states they satisfy phi, we call it stat phi, we denote it by this. Okay, it's essentially the set of states in the Fouquet structure which satisfy phi. Yeah, it's a set of all states, and this is computed recursively. When I say computed recursively, what do I mean? So phi can be, it's a big formula, it can have sub formula. So first you start computing with the set of atomic propositions. So for example, if you have an atomic proposition, let's say in the formula phi, there is an atomic proposition A that is appearing. So you will first compute what is the set of A, right? And then you will see that where all this thing is appearing, right? You can kind of look at the parse tree of the formula, right? And you start bottom up. Okay, you look at the parse tree, you start bottom up. So you look at all the smallest sub-formulas, which is like at the leaves you have the atomic propositions. There can be a negation, like maybe an internal node is negation. So you then compute the set of states which satisfy the negation of this formula, which is like the negation of this formula is like the complementation of the set. Okay, to do it like that. So that's what it says, the bottom-up traversal of the parse tree of a CTL state formula phi. Right? You first look at all the subformulas. For each of these subformulas, you compute the set of states that are satisfying this subformula, and then you are kind of going up the tree. For example, if you have a conjunction, you have like, let's say you have phi 1 and phi 2, a formula like this, phi 1 and phi 2, right? So you compute sat of phi 1, you compute sat of phi 2, then what do?
Intersection.
Take the intersection of that, right? It's essentially a set of states, you take their intersection, right? So like that. So you take the parse tree, the inner nodes are labeled with an operator. For existential normal form, these operators are of this form, right? It can be a negation or a conjunction or an exists x, exists, like there exists a path where the next state satisfies something phi, right? If it's of the form E exists x phi like this, okay? And then you have exists until, and you have exists globally, okay? In the ENF, you have these things, right? So why do we have this? Maybe let's just go back. So you have this exists globally, okay? So these are the things that we have. We have exists next, we have an exists until, and we also have the exist globally separately. Why? Because of this. Like when we are having this for all phi 1 until phi 2, so we are getting rid of the for all paths. So we are introducing an exist globally here, right? So this is part of the existential normal form. Right? So this is the thing, and so I'll talk about it in the next class, that how we compute for each of these operators. Okay. So let me stop here. And are there any questions? Vishal, any question?
No. So
No?
the reason why this is incomparable is because for every temporal operator we need to quantify, right? Otherwise it will be like strictly powerful because we have something more.
So one of the things is that, like you see here, syntactically, I am only allowing, there is a restriction. The restriction is like I am allowing uh, this alternation of the path and the state quantifiers. I mean the state formulas. The path formulas and the state formulas, they alternate. Okay. Which is not the case in LTL. Okay. Now, this, for example, also adds a restriction to CTL when compared to LTL. So this is one thing. So there may be certain cases where there are formulas which are, I mean, there are properties which can be expressed using LTL but cannot be done with CTL. And as we saw that there are certain this kind of possibility, right? For all computations, it is always possible to return to that initial state. This kind of things you may not be able to express with LTL. Okay, so there this incomparability comes. Now, if, for example, if you remove this restriction, that this alternation restriction, okay, then you will find a logic which sort of captures LTL also. It will be strictly more expressive than LTL. Okay. So that logic is called CTL star. So we'll just briefly talk about it. So this logic is called CTL star, where we don't have this kind of a restriction. Is that okay?
Yeah. Makes sense. So there is another logic which
Yeah, there is a logic which captures both LTL as well as CTL. Okay. And it's essentially like if you like do not put this restriction of this alternation, then that will be more expressive, strictly more expressive than LTL.
got it. Makes sense. Nice.
Okay. Okay, so let me stop the recording.